Okay, we are now at a point where we can go over our labelTreeAux function again and our counter type again, and we can try to come up with an abstraction that allows us to capture the recurring pattern that occurs in this function. And this time around, we already know where we want to end up with. So we're in a slightly better situation. So let me again define some form of funny bind operator, right? Something like this for the time being. And let me write down the type signature that we would expect this to have. So we are planning to somehow find a sequencing for counter-maintaining operations returning a value of type A. And we want to sequence them in such a way that if we have one computation that maintains a counter and results in an A, then we can combine it with a second computation that gets access to the result of type A and can itself continue maintaining the counter. And then we get a combined counter maintaining operation of type B out. And the idea is that the value of the counter initially goes into this first computation, and then the final value of the counter coming out of the first computation is threaded for us behind the scenes to the second counter maintaining operation. And the final value of the second counter maintaining operation is also going to be the final value of the overall computation. So in order to do this, we get a computation, let's call it comp, and we get a rest. And we do want the whole thing to look somehow similar to how it occurs here, so that we can match it up, so we can use this as orientation. Although I have already said it's not going to be such an exact match as in the maybe case, and that is primarily due to the fact that we still have these constructor applications that, I mean, I could rewrite this even further to make it match up even more closely, but that would make this definition look even more awkward. So let's just try to see whether we can get there. So we have to produce a counter, a combined counter. So it's obvious, and it also fits with the fact that here on the right-hand side in the bin case, where we have the main action going on, right, we start with a make counter invocation, and we get some incoming counter value in. So let's try to start with this. And then we want to feed this incoming counter value to the first computation. We can feed a counter value to a computation to something of type counter of A by using run counter, because if we call run counter on comp, then we are turning something of type counter A into the function from int to a int that this counter type wraps. So if we call run counter on comp, then we can pass C0. And this matches roughly what we're doing here in this let. Right? We are calling some computation. In this case, the first computation we're calling is labelTreeAux L with the incoming counter value. And then we're pattern matching on the result. So let's just do this here as well. Let's just do a let, and then we get two things out. We get a result of type A in this case. So let me just call it A here. And we get a new counter value out. And now we have the rest. So, and this, I mean, this part actually does match what we have up here rather nicely. Now we have the rest, and we somehow have to get the rest into the right shape. So the rest is at first a function that expects something of type A, and we do have something of type A now, so we can apply the rest to and the result we're getting here of type A in order to get something of type counter B. But what do we actually need at this point? At this point, we don't need a counter B, we need a B, int. But a counter B, if we do this application, a counter B wraps up a function that goes from int to b, int. So we can run this counter again and feed it a new input value, and that should be the C1. This is exactly the threading that we're expressing, and then everything works out. And now this doesn't precisely match what we have down here, right? So that means that we have to somehow, if we apply the bind function in here, we have to rewrite the code in such a way that the rest then matches. But we'll see how that works out. But nevertheless, I mean, this first part matches rather precisely, right? Up until here, effectively. And then we should be able to like rewrite the rest of this function so that we can still like replace this part of the code here, this first part of the code, with one application of bind, and then have the rest in a particular form. And then perhaps we can do it again. So that's what we're going to try now. But at least this version of bind is type correct, it type checks, and it also makes sense in the sense that we do express this threading of the counter in the way that we set out to do, right? We have an incoming counter value, we first feed it to the first computation, then we get a resulting counter value out, and that we then feed to the second computation, which additionally can also depend on the result of the first, on the proper result, the non-counter part of the result of the first computation. That is what this version of bind is doing. So let's try to do this rewrite, okay? So at this point we have a type correct program, just to verify once more. And what we want now is basically to get rid of this make counter C0, because that's part of our bind invocation, and basically everything up to this point here, labelTreeAux, oops, that was too much, labelTreeAux L, that is the first argument of our first invocation of our fancy counter-based bind. All right. And then we are using a lambda abstraction again, and the lambda abstraction is going to pick up the result of the computation, and that is now the non-counter part of the result, so the relabeled tree in this case, right? So the new L, that is what we're picking up. But now at this point we have to turn the rest of the computation, the rest, into something that is of type counter again, so that the bind function can apply run counter to it. And we can do that just by calling make counter at this point again, and picking up the current value of the counter that we are getting at this point, and then putting the rest back into a let. And now we are at a point again where we have a type checking definition again, so this part type checks, and we have been replacing the first part of what we're doing with an invocation of bind, and the rest is still in the shape that we had roughly before, where we have a make counter call that wraps all the rest, that picks up the counter explicitly, and we have a let in which still has a couple of things to do. And now we can apply bind again. And note that in this first part that we've already rewritten, we're not mentioning the counter anymore. That is the real achievement. So we are not calling make counter. We're not having any variables called C something. We're only saying we want to label the left tree and we want to call the result new L. Okay? So this is what we're going to try again. Now the next thing the first argument of the second invocation of bind is going to be the thing that we call run counter on here, step counter in this case. So step counter is going to become the next comp, right? And the next result is LX. So let's just do this. We delete everything up to step counter. Then we move step counter on a new line. And we call the result LX. Right? And at this point, we now again have to produce a counter. So we have to apply make counter again temporarily, pick up the current incoming value of the counter, which is C2, use an arrow and put the rest back into a let. And now we have been rewriting the first two operations. And the first two operations actually do not explicitly mention the counter anymore. Right? We are not passing any C variables around anymore. All the threading is now done by the bind. All right? And actually, even in this intermediate state, the function still works. If I call labelTree on my example, it just produces the correct result. And labelTree is defined in terms of labelTreeAux, which is my partially rewritten labelTreeAux. So all these intermediate stages, they all work. We never are at a stage where the function stops working, right? And now we can do this whole thing again. Now we still have a computation here, labelTreeAux R, right, which is again fitting the shape of our bind operation. So I can do the whole stuff again. So delete everything up to labelTreeAux R. Put that into the bind, call the result new R. And then we have to put the rest into a make counter call again. At this point, the current counter was called C3. And now we don't need a let anymore. We just have the remaining computation here. And now it's actually probably nicer to put this part of the computation all on one line here. All right. And now I think we are at a point where I would say things have actually become nicer already, because we are hardly mentioning the counter anymore, right? And we are not having this manual threading of the counter anymore out in the open. It's all in the background. It's automatically threaded through the computations. The outgoing counter from one part is going into the next. So we no longer have to pay attention to us doing it correctly. The only point where we're accessing the counter is in the step counter function. And the step counter is going to give us the current value of the counter and automatically incrementing it by 1 in the background, so that labelTreeAux R is not going to reuse this value LX that we have extracted here, which we are then using to label the current element. We still have two places where we are mentioning the counter, and that is in the empty case and here at the end. And if you look at it, they both follow the same pattern. They actually take an incoming counter and then not use it. They just produce the same counter value as the output. Here we take C3 in and we put C3 out, and we're not using C3. Here the same thing with C0. Now, because we know where we are going, we have now defined a bind function for counters. But we haven't really defined a return function for counters yet. And if it's true that this follows the same pattern of a monad that we have now already seen in the context of maybe, and before that even in the context of I/O, then perhaps we should also have something like return in the world of counters, saying that if we have something of type A, we should also be able to turn it into a counter maintaining computation of type A. And remember that return was always about not exercising the option, the additional option that was given to us. In the context of I/O, return was saying we lift something into the world of I/O without actually doing side effects, even though we could. In the context of possibly failing computations, as modeled by maybe, we were lifting something into that world by saying, oh yeah, but we actually never fail. And here we're giving the option to access and modify and maintain a counter, but we actually choose to just leave the counter alone. And so return counter takes some x, or perhaps I should even just call it a, and then wraps it up in a make counter, and the make counter gets a counter, c, but then we just return a as the result and the same c as the outgoing counter. We don't change c in any way, and we don't use it in any way. And this fits the type of return counter, and it also fits exactly the pattern that we have up here, right? In both these cases. So we actually can write this as return counter empty. And this as return counter of the combined binary tree. And now we really don't mention the counter anymore at all. Right? Really, the only place where we're doing something with it is step counter in the bin node, where we are incrementing it by 1 and accessing the current value. Right? But apart from that, we're just passing it on, we're just threading it on, but we don't have to do much work for it anymore. It's all hidden behind the scenes, and the potential for making mistakes with it is gone by this. It's still totally explicit because the type of our function is counter, and the definition of bind, we can look at it, does tell us exactly, precisely how the counter is threaded. So there is no magic, it's just hidden a little bit so that we can focus on the structure of the computation. We have that out in the open, and that the potential for making mistakes is removed because the threading is automatically done always from one computation to the next. It cannot easily be mixed up. So we should try out that this final version also still works. So let's call, after reloading, labelTreeAux example yet once again, and we see we still get the numbering 1, 2, 3, 4, 5, 6. And perhaps I should also make a change for so just to show that we are really using this version. So for example, I could add another call to step counter here and just drop the result. What would that change? That would basically mean that we're always stepping the counter twice in every node, right? And then we're discarding the result of the first step counter, and then we're using the one of the second. So then we would get everything numbered in steps of 2, like with the first node being labeled with 2 and the second one with 4. So let's see whether that actually happens. It does, right? Or we could say we want to change the order of labeling from right to left. So then we would do the labelTreeR in the beginning and the labelTreeL in the end, and the step counter still in the middle. Now if I reload this, I get everything labeled from right to left. So the rightmost node gets the 1 and the 2 and the 3 and the 4. And consider how much more difficult this operation would have been if we had done this before, because we would have to rewire all the threading ourselves. But now it is automatically done correctly for us. Yes. We're still not completely done, right? Because we are using our own version of bind. We're using our own version of return. We would like to make counter an instance of the actual monad class. Unlike maybe, which is a data type that's already defined in the prelude, right? So we have it available, and it already has a monad instance in exactly the expected way. The counter type is a type that I've defined here on my own, and it doesn't have an already existing monad instance, so we would have to define our own monad instance. But that is where we're running into some technical difficulties, because as we had seen before, the monad class has an applicative constraint, an applicative superclass. So if we do the naive thing and just say instance monad counter and say the bind, we want to define that to be our fancy bind, and possibly even the return, we want that to be our return counter, right? Then we still get an error message here that says, if we scroll down far enough, that there is no instance of applicative for counter, which is arising from the superclasses, because if there is a superclass constraint, it means that if we make something an instance of monad, we also must make it an instance of applicative. So in the next video, we're going to actually complete this. We're going to see how we can make our counter type an actual instance of monad by walking up the hierarchy and defining all the other instances as well. Okay.